Okay, so we're going to kind of do one other version of solving for this. So I want you to note that we can also use work energy to solve for these problems. If we want to find the velocity as a function of x, right, we can use work energy. If we need velocity as a function of time, we need to look at these second order differential equations when we're dealing with harmonic motion, okay? Or if we want acceleration as a function of time. Um, so, but when we're looking at it as a function of x, we can actually solve this problem a different way. And let's look at what that means. Okay, so all right. So I have a hanging spring. So same type of problem, just sort of a different approach. So I have this hanging spring with this mass. And we're going to say that this was my equilibrium position, right? With the mass. So this is my equilibrium position with, normally when we're given it, it's the equilibrium position that has been displaced down by the actual mass. And we're going to pull it down this extra a distance, right? And then this a distance is going to be the amplitude that it oscillates with, right? Up by this negative a and this positive a, basically. Okay, so it's oscillating back and forth, up and down, based on the distance that you kind of like shifted it down by. Cool. Okay, so let's look at conservation of energy. So we're going to look at the energy in, right? Uh, so the initial energy is going to be equal to PE plus KE. So this is kind of cool because we're going to be able to look at kind of what's happening with the system. Okay, so our initial energy in, so we're going to say at the bottom, we're going to call this like 0.1, right? At the very bottom, when we pull it down by this A, our total potential energy before we release the spring and it springs up is going to be equal to 1/2 KA squared, okay? And then our potential energy is 1/2 kx squared. And this is our potential energy at any time, right? So what x is like some distance, right, away. So x is like usually smaller than a, right? So negative x or of x. So you can, these signs could be different, I guess, depending on how you model your problem. So if you want to model the a as positive going up or positive going down, it should just be related to the direction that the spring is pulling. So I might have mine backwards, but I think that's okay. Let's go through the whole thing and then I'll correct if need be. Okay, so 1/2 mv squared. Okay, so then this is my kinetic energy. So what I'm saying with this is that I pull down the spring with some initial energy at the bottom, and I'm going to let it go. And throughout the oscillation of this mass, as it's going up and down, this initial potential energy is going to be converted in part to some other potential energy that's going to depend on how far away, how far x is away from this center line, this equilibrium point. And then I'm going to have some kinetic energy as well. So at this center line, my potential energy as it passes through, each time my potential energy as it passes through is going to be 0, okay? Which means that I'm going to have all kinetic energy. Then as I come up to the top here, once I reach the top of my oscillation, I'm going to have all potential energy again, where this x is essentially in magnitude equal to a. And then my kinetic energy is going to be 0. So it's going to stop at the top, right? And then come back down, stop at the bottom, and then come back up. So the highest velocity is in the middle, and it's going to kind of oscillate up and down. Okay, so now all I just really want to do here is rearrange and solve for velocity because I was asked to find for velocity as a function of, get an equation for v. Yeah, so I'm going to find velocity as a function of time using conservation of energy. Okay, so I've got this guy. So my initial energy is potential plus kinetic, and then algebra. Okay, so I'm going to cancel all the halves because they're all multiplied by 1/2 kx squared plus 1/2 mv squared. Okay, so let's do, so I'm just going to move things around here. So I'm going to have k times a squared minus x squared, right? Because notice they both are multiplied by k. So I'm just going to kind of, I'll have this a squared minus x squared, and then I'm just pulling the k to the outside. So I did that all in kind of one step. So sorry if that was a little confusing. Just want to point out what's happening. Okay, let's see. Oh, why did I leave that 1/2 there? I apologize. I took them all off the other ones and then I left that for some reason. Okay, so k over m times a squared minus x squared is equal to v squared. And I'm just going to kind of switch the sides of the equation to make it more readable. So v is equal to the square root of k over m times a squared minus x squared. Okay, cool. So we used conservation of energy to solve for an expression, velocity as a function of time, right, of this spring. So we want to find the velocity as a function of position. So I know, if I know where it is, I know what its velocity is, basically. because I can tell how much kinetic and potential energy it has. So if I know where it is in relation to a or x, in relation to a or x, I can just solve for my velocity. Not too bad. Okay, so what about acceleration? Well, we kind of talked about this a little bit earlier, but we're saying that, so if I know my F is equal to negative kx, right, my spring force, Fs, and then I know that F is equal to ma, right, and this a being mx double dot or whatnot, but we know that that's our acceleration. We're just going to solve for an expression for acceleration. So we're going to say F, so we're going to say ma, right? Ma is equal to negative kx, right? So the acceleration is going to be equal to the change, or the spring constant multiplied by x. Those two forces are equal to each other, but there is some net acceleration, right? So the acceleration is going to be, we're going to have this a is equal to negative kx over m, right? Okay. So that's our final solution here. So we could also have like this as, so actually technically this would be like x of t here. Yeah. So yeah. So we're balancing our spring force, right? So the spring force and then just the acceleration. But this acceleration is still changing with respect to time. So kind of keep that in mind. So acceleration is a function of x. But if we know what our x is and we plug it in, we could find our acceleration essentially at that point. Okay, so yeah, using work energy. So again, these solutions are posted for both of these. If you have questions, let me know. I'm gonna go ahead and move on to the next question.